Okay, so I'm James Munns, and this is the Internet of Streams project. This is planned to be a series of streams to build a wireless sensor node platform as a side project for my house. The idea here is to kind of condense all of the all over the place side projects that I find myself working on into a single project where I can apply them all in one place and to showcase some of the stuff that I like doing in embedded systems and IoT development and what's possible in embedded Rust today. So, we're going to be working with a board called the Decawave DWM 1001, and I'll have links in the repo for this. And we're going to be making it an IoT device. So, building up the software for it, get it talking from one device to another, and figure out something interesting to make it do in my home. So the idea of this stream, and this first episode isn't a stream because I haven't turned on my YouTube streaming ability yet. So this first one's going to be recorded, and then the rest of them should be streamed and then also put up on YouTube. But the goal for this stream is to kind of showcase what is possible today in embedded Rust and to show off some of the already existing libraries and the stuff that's out there, but maybe if you haven't done embedded Rust you haven't seen, or even if you have, you just haven't run into these libraries before. The focus of this stream is not so much making a perfect embedded IoT system. There's no plan to commercialize this or make it an actual official product, but instead focus on teaching. So my background is in embedded systems. I've developed a lot of stuff, everything from software for airplanes to IoT platforms for companies and things like that. So I wanted to share a little bit about my experience with developing embedded systems, developing specifically in the Rust programming language, and the side of development that comes with IoT development. So when you have connected, low power, constrained systems and getting them all talking to each other and interfacing with sensors and monitoring the real world in a bunch of different ways. So we're going to be using that dev board that I talked about, and I've got a link to the product spec for it, but this will all end up in the repo. I've already picked out a couple libraries we're going to be using, but the idea is to keep this all in one repo and to have almost all of the work that's done in this repo be streamed. So anyone can kind of go and look at the code, and then if they want to figure out why I did something or how I did it, then they can go back to these streams and, follow along. I also hope that this will inspire me to actually write some blog posts and things like that explaining some of the concepts in more detail. So if you're ever watching this and you want to know why I did something or how I did something and it's not clear from the stream, just let me know and I'll probably write a blog post about it. So I've got a link to the project here. It's called the Internet of Stream project. So I'm hosting it on the Fair Systems GitHub space. So I work for a company called Fair Systems. We do consulting and training for Rust at the systems level. So that means things like embedded systems, things like distributed databases, things like operating system and driver development. So if you have interest in those things and you want to work on that on something other than a hobby project, let us know because we're happy to help out on that. But this is meant to be more of an intro for people who either haven't developed embedded systems before or haven't developed Rust before. So I've got a whole laundry list of stuff that I know I'm going to want in my ideal IoT platform. I mean, for my wireless sensor node, I'm going to want it to be able to do wireless communications. So I'm going to have a bunch of these nodes, and they're going to need to talk to each other, and then probably talk back to some kind of computer, and maybe even remotely over the internet in some way. I'm going to need a bootloader or over-the-air updates, so I don't have to go and manually program all of these nodes after I scatter them around my house. So I can just run a script on some computer and push the newest firmware to all of them securely, hopefully. Some of them I'm not going to want plugged into the wall all the time, so I'm going to want to support low power mode. So putting a rechargeable battery on each of these and scattering them around my house, and then hopefully not recharging them too often. I really don't want to be taking them off the wall every day, so I'm hoping I can get months of battery life out of most of these devices. Some things that are going to be really helpful for development, like the ability to do logging. So this board happens to have a serial port that goes out over USB, so we'll be able to print messages while we're developing and see what it's doing, and then probably at some point we're going to have to debug some stuff. So logging is going to help with that. We're going to set up continuous integration, so the ability to make sure that everything that we check in actually does build, and I don't accidentally push a bunch of broken code that does work on my laptop but is going to be confusing for everyone else because it doesn't actually build or work. Probably end up doing some unit testing. So unit testing is something that's done in a lot of other areas of development, but on embedded development, because you're writing software for a totally different system than your build system or your laptop that you're developing on, unit testing is a little bit different, but definitely still possible. So we're going to be looking into that at some point. We can even go further and do something called hardware in the loop testing, which means we're not just unit testing the code, we're actually testing the whole system. So that might mean plugging some other microcontrollers and things like a Raspberry Pi into our system to make sure that it's really doing the stuff that we think that it's doing. I'd like to get to some more advanced network protocols, so things like 6LoWPAN, which is IPv6 for constrained devices. So instead of just having all of these sending one-shot packets from one device to another, that they actually act like a network. So you can send messages from one to another and then even do things like mesh networking. So if the radio of my wherever I plug this into a computer isn't strong enough to reach all of the devices, that's okay, because the other devices will pass on messages and I can address them kind of over the internet. This device actually has two radios on it. It's got an 802.15.4 6.5 gigahertz radio on there. That's the Decawave DW1000. It's a really cool radio because you can not only send data over it, but because it's so high frequency, you can do things like wireless ranging down to an accuracy of 10 centimeters. So if I have something connected to something that moves around my house, like me or my dog, then I can track how I'm moving through my house and even when I'm in my house and leaving my house. This chip also has Bluetooth on it because it's got a Nordic NRF52 on it, but we're not going to use that quite yet for a couple reasons, and we'll get to that a little bit later. At some point I'm going to need that way for one of these wireless radios to talk to a computer, so that's what I would call a gateway router, where I'm going to have one of these radios hooked up to my PC at home or a Raspberry Pi or something like that, and that's going to act as the place where all of these low power devices can actually connect up to the internet, or when I'm connecting in from over the internet, that I can talk to all of these devices. And I'd like to have some fancier messaging and define some kind of protocol and make some kind of convenient serialization and deserialization of messages so we don't have to do that manually. Right now we're just going to be sending packets to each other, so it acts a lot like UDP, if you're familiar with UDP, where we're just going to be able to send messages and they'll probably show up and some people will hear them, but if we want something a little more reliable in terms of communication or the ability to send like really long messages that need to be broken up over other packets, we're going to need some kind of protocol for that, or some kind of even just a way to command different systems to do different things. So these are all things that I'd like to do in the long term, so maybe over the next weeks and months, but we're going to be picking kind of chunk of those at a time and starting to work on them. There's probably going to even be other stuff that I haven't mentioned, like I'll probably just go find fun sensors and displays and things like that that I want to play with, and once I have kind of this test platform that we've already set up, it makes it really easy for me to just solder on or plug in a new device that I want to play with, write a driver for it, and then deploy it somewhere in my house. So I could have a screen next to my door, I could have a temperature and humidity sensor next to my bed or something like that. So we'll probably find those as I'm interested in them, and I'll find a use for them. Like I said, this is not a real product, it's just a project, so whatever I find is interesting is probably what you'll end up seeing me writing code for here. And the idea is really to kind of concentrate all of my efforts into one place, so I spend a lot of time with one project instead of a lot of little projects, which are what my side projects end up being. And hopefully this will be a good showcase of a medium to large size embedded project in Rust, so people can use that as a reference and somewhere to start if they're looking to build something a little bigger than a Blinky light, or just working with one sensor locally and things like that. So for today, my goals are a little simple because this is my first stream or recorded video, but the goal is to get the project set up. So right now, over in my terminal window over here, I've got pretty much an empty folder. So I made a Git repository for this project, and you see the notes file that's sitting here. I should probably go ahead and save that. So I've got my saved notes file here that lives in the repo, but we don't have any code, we don't have anything else. So we're gonna go ahead and get the project set up. Once we have some actual code in there, we'll get our CI testing set up. For now, we're probably going to use Travis CI. That might change in the future, but for now, we'll be doing kind of some basic testing on Travis CI. We'll get the hardware abstraction layer, or the HAL, set up. So this is the library in Rust that knows how to talk to our Nordic chip, knows how to talk to our radio, because that's already been written, so we can pull that in as a dependency. And then there's a sort of real-time operating system. It's really an event-driven concurrency framework called RTFM, or real-time for the masses. That's a really convenient way to write concurrent, efficient, and safe software in Rust. So we're going to be using that for this project. And then the goal for today is generally to blink our first LED. So if we get all that other stuff set up and we can blink one or a couple of the LEDs that are on this board, then we'll go ahead and do that. I'll go ahead and give an intro of our board. So like I said, this is a dev board from a company called Decawave. They make this module called the DWM1001, which has that 6.5 gigahertz radio, so that's that funky antenna up here. It's got Bluetooth from a Nordic NRF52832. So that's what that little chip there is actually a 2.4 gigahertz antenna, and I hope you can see that. So the antenna and the chip, and this is the module, and then the rest of this green board is the development board. So it's got things like a debugger, it's got a bunch of LEDs, it's got some buttons, it's got a USB port that's hooked up to the debugger, so I can flash code using USB and then also talk over the serial port. And it actually even has power management and stuff on it. So it's got a little connector here for a lithium battery, so I could plug that in and leave it somewhere in my house, and hopefully it'll keep talking over the internet even when I have it unplugged over my USB. So we're going to go ahead and get started. We're going to be using a couple of those packages that I mentioned. So the first thing that we're going to do is we're going to go ahead and make a new project using Cargo, which is Rust's build tool. So we'll make a Cargo new. This is going to be a binary project, and it's going to be called, let's just call it sensor node for now, because I think that's what it's going to be. So we've got a new sensor node project, but Rust does let you make new projects, and I can do things like cargo build. But the kind of default stuff that's in there, let's do a refresh. For some reason my editor isn't picking up this new file. There we go. But the thing that it's generated is a normal desktop program, and for embedded systems this isn't exactly going to work. So what I'm going to do is I'm actually going to go out, because I know the hardware abstraction layer that we're going to use, this Rust DWM1001 repository, has some examples in there. So I'm actually going to go ahead and just borrow some building blocks from the library, because they've been very helpful and provided all of these things. So I'm going to make sure that I'm grabbing all of those. So I will need to look at the cargo toml. Let's see, yeah, that's a good point. I should probably go in here. This is sensor node. Okay, it's got my name. We are going to be using the 2018 edition of Rust. And just to start, I should probably go ahead and put DWM 1001, and there's recently been a release of this, so we're going to use the 0.1.0. I know we're going to need that, and then we'll need to tell Cargo that, hey, we're not building for a desktop. Even though you're running on a desktop right now, that's not actually the target that we're going to use. So we're going to need to go ahead and create this cargo config. So I'm going to make dir.cargo touch cargo config, so I'll go ahead and make that file, and I'm going to paste it. So what's in here is saying, hey Cargo, every time you build this project, the target that you're going to use is thumb v7em none iabi hf. So the actual chip on here is a Nordic NRF52832, which is a Cortex M4F. So this kind of says the M4 thing. These are kind of the parts of the ARM chip that are there. So these microcontrollers have a bunch of different options, but this is specifically the one that matches with our chip. And then this HF on the end means that we're going to be using hard float, because this chip has it. I'll explain some of these other commands later when we're ready for them, but we're not totally ready for them yet. So this is here, and now Cargo knows that we're going to be building for an embedded system. And then I will need to go to, very handily, there are some examples in here. So let's just start with the blink example, because I know this one's going to work. Although we're not going to use panic semi-hosting. So we're going to make some modifications here, but this is a good place to start. So let's say goodbye to that main, and we're instead going to use panic halt, which is a crate that I know, but I can't remember what version that is, so we're going to go crates.io, which is the package manager for Rust, even for the embedded stuff. And we're going to go look up that panic halt crate. So what the panic halt crate, or what these panic crates do, is they tell the embedded system what to do if Rust panics. So normally if you're on a desktop and Rust panics, then your program's just going to close. But we don't have an operating system here, so we kind of have to be a little more specific on what we're going to do. So we're going to go ahead and use the panic halt crate, which just says if something goes wrong, then just stop. So the processor will just stop whatever it's doing and won't go any further. I also know that we're going to need the NB crate, which is for non-blocking, which has some cool traits for non-blocking I/O, but we're just going to go ahead and pull this in for now. So I need this. What else do we have in here? I've got the DWM 1001, which includes kind of all the stuff that we need in here. So this should be most of what we need to get a hello world. And we're actually going to be cheating a little bit because we're going to skip right to the end where there's LEDs. But I want to make sure that my project is set up right and it actually builds. So I think that's everything we need here. Let's see what happens when we do a cargo build. So cargo is being very helpful, and because all of these packages are available out on the crates.io repository, that it is possible to pull all these down automatically. And right now, we're blocking on the file lock from my build directory because when I hit save, my editor went out and did a cargo check because the syntax highlighting kicked in, and because this is a new project, it's going to be silently building that in the background. So I can go ahead, and while that's working, I can explain some more of these pieces. So kind of at the top of the file, there's two big lines. So in Rust, whenever you get this crunch bang here, this means that these are attributes that apply to the whole project. So this says no main because we're not going to be using a function called main. There's some macro magic going on here which sets the entry point for an embedded system, so we need to tell cargo, hey, don't worry if you don't exactly see a main function, we'll provide it, don't worry. And then no standard, which means we're not going to be using Rust standard library because we don't have an operating system or anything like that. We really can't use the standard library. This next line says that we're going to use a crate called panic halt, which, like I said, is when we run into a panic, like when we unwrap something and that's wrong, Rust is going to panic, and we've defined the behavior now as just halt. So it will sit there and basically go into an endless loop wherever it is. There's this crate called Cortex MRT, which is a lot of the glue logic for building a Cortex-M application. So specifically, it provides the macro that says, hey, here's the entry point for the program. This DWM 1001 crate has kind of the whole hardware abstraction layer for this board. So it contains a couple different building blocks. So specifically the DWM 1000 radio driver. It has a hardware abstraction layer for the actual 52832 chip. And then those even contain some lower level primitives. And then we've got this non-blocking crate, which normally tells you how to perform non-blocking I/O operations. But for right now, just for the easy example, we're only going to be doing the blocking version of non-block. But that's okay for our Blinky example. So you can see cargo's gone ahead and kicked out, and you can see it's actually pulling in a bunch of different dependencies. But because these are all managed by the package manager, we don't have to think about it. I don't need to set up a bunch of Git repos. All of these crates are just checked in, and in Rust, crates are libraries. So these crates have all been pulled in for us, and they're going to go ahead and build. So, right, I forgot to set what the Cortex-M RT is, so I'm actually going to go look at what DWM 1000 uses, just to make sure that I only have one version of this right now. But this is using 063 of Cortex-M. So I'm going to add that to my cargo toml, and we'll go ahead and add that. And let's go ahead and do a build again, and then no field LEDs. So maybe these changed. I should probably file an issue. Let's go look at what they're calling these now. So this is actually the crate and LEDs. LEDs, pub LEDs. Right, I forgot to enable the feature. So there are actually, I need to turn some features on. So in Rust, instead of having like pound defines or having to set things in a makefile, Cargo has a built-in way of setting different features. And by default, a lot of these features are off. So these are the ones that I want. So I'm going to need the dev and the RT. So what we're going to do is we're going to cut this out. And we're going to do dependencies dot this. That's not what I wanted. But we're going to move that there. So we're saying that this is that, and then our version is that. And the features we're going to use are dev, which says we're on a dev board, and we really do want to use everything that's on the normal dev board. And RT, which is the runtime. It's not quite exactly the same thing as a runtime for a desktop. This is just saying for that Cortex-M RT crate, pull in all the extra useful things because we're going to want them. So we go ahead and save this, and let's do this. Actually, what we're going to do, we're going to do Cargo. There's a cool tool called Cargo Watch, which means every time you change a file, it's going to run this command. So I'm going to tell Cargo Watch to do a build every time we have that. So again, because we've pulled in some new features, it's going to have to recompile some stuff, and my text editor has gotten ahead of me. So let's take that time to clean things up, and I'll start explaining the code here again. So this is the main. In an embedded system, the main actually has the return type of the never type, which means we're telling Rust that, hey, this function can never return, because in an embedded system, it doesn't make sense to return from a main because you're not returning to anything. So we then get a handle to our board. So in Rust, the way you represent access to the hardware is by getting an object. So the hardware abstraction layer has this function called take, which says just once you can go and get a handle to the hardware, and that's why we're unwrapping it, because if we did this once, this is going to work. If we did this a second time, it says, nope, I've already given you a handle to that, and this is actually returning a result. So the unwrap is going to either give me the item that's in there, or it's going to give me an error, and when I unwrap that, my board's going to crash. But we're only pulling it once, so it's okay. Then we're going to do some things like set up a timer. So we'll take one of the raw hardware level timers, and you'll see a bunch of these methods called constrain, which that means that we're taking a low level peripheral and we're turning it into kind of a high level interface. So Rust has this concept of ownership. So to make sure that we have things configured right and that certain parts of the code can only access what they need, we force things to be passed around. So we're trading kind of a low-level raw interface to this hardware to a high-level kind of abstracted level to this hardware. Then we'll get into the details of this a little bit more. But then we just go into a loop where we turn an LED on, we wait 20 milliseconds, we turn the LED off, and we wait 230 milliseconds. So we should get a 4 hertz blink. So this is built now, which is actually great. So we actually need to do one more thing, because to load code on here, we need the ability to, well, we have a couple missing things. So the first thing that we're missing is we need a way to connect, and we're going to be using GDB, which is the debug protocol that's used in a lot of other desktop applications, but you can use them for embedded systems too. But we need something that does the translation from GDB, which operates over a network port, and our actual hardware, which is connected to our laptop on a USB port. So there's a tool called this. The debugger chip that's actually on here is one from a company called Seger, and it's their J-Link product. So we're going to use their application, which is J-Link GDB server. The device we're using is the 52832. We're going to be using the SWD interface, not JTAG, and we're going to set the speed to 4,000 kilohertz. So that should connect if I remember to plug my device in. So devices work better when they're actually plugged in. So I've got a red power light now, which makes more sense. So this is connected. So now we've got a connection, and it's listening. It's got a GDB port open on port 2331 of my laptop. So that's the other thing I forgot, is from this template, we need to go out and get the GDB script. So this is going to say, every time I run a debugger, I want you to run these commands first. And this is going to automate the connecting to the device, loading the code to the device, and then starting the firmware image. So we're going to go ahead and touch debug.gdb, and And then we're going to go ahead and copy and paste things. This 3333 is typically used if you use an adapter called OpenOCD. We're not going to be using that. We're using the JLink GDB server. So I'm going to change this port to 2331. It says, hey, the target we're debugging is somewhere else, but you can talk to it on port 2331. Then I want you to load the code that you've built, and I want you to immediately begin running that code. So I'm going to hit save. And then when we go back to this cargo config, this is that runner part of it. This is saying, when I type cargo run, instead of just executing the program, call this command. So we've got the GDB that's specifically for bare metal systems, so this ARM NUNIABI version of GDB. We're going to be using the TUI, which is kind of a ncurses style interface into this. Quiet, don't give me a bunch of debugging output, and then specifically launch with this script. So this is saying build that script. This other stuff we haven't talked about are linker arguments, which is saying use a linker script. But because we haven't modified any weird settings, actually the libraries that we're providing already provide a linker script for us. So we're just going to keep using the default linker script. So this link.x is going to come from that hardware abstraction library that we pulled in. So now if I do a cargo build again, yep, that still works. If I do a cargo run, you can see that we've launched code, and actually you can see a blinky LED. So in this debugger, I could hit Control C, and you can see that it's decided to stop in some part of it's waiting. So that makes sense. It's in the delay function because everything else we're doing is super quick. So the delay is really the only thing that takes time. But I can step through this code. You can see that that longer delay does actually delay a little bit longer, but we have the full ability to step through our code. If I wanted to look at the assembly, and if I wanted to step through the actual assembly instructions, I could do that. You don't always want to do that, but yeah, but you can. But cool, we've blinked our LED, so this seems like a really good time to quit out of our debugger, and let's commit. So I'm going to do git add -i. We are going to add, oops, so yeah, there's a bunch of, that's not what we want. We have all of our build artifacts in there, and that's not what we want. So I'm surprised. Oh, I guess because we're already in a Git repo, aren't we? So let's make git ignore. Let's make a git ignore in this folder that ignores everything in the target folder. Great. So now let's try this again. Great. That makes more sense. So I'm actually going to add my notes because my notes should be in there. And then we've got our cargo config, our git ignore. Because this is an application, we are going to check in the lock file. This says we're using specifically these versions of these libraries to make sure that when you download it, you're going to use the exact same versions of the libraries that I am. And cargo.toml, our debug, and our main.rs. So we're going to go ahead and add all of these. And let's commit this. And this is initial skeleton blink of sensor node. Great. So I've got that committed now, so I feel very, very good and safe. So I modified some stuff. What did I modify? Oh, I'm just removing some white space. That's fine. Get rid of this, and actually I know, because we never directly use the halt function, it's going to complain that we have unused libraries. So I'm just going to say allow, what is it, unused imports, I think. So now if I do a cargo build, cool, it doesn't complain at me. So yeah, we've got that. So the other thing that we need to do, so let's go back to our notes. So we've got, so that was to do. So let's to done. It's the opposite of to do is to done. So we have our project set up, and we've blinked an LED, but we're actually going to change some libraries that we're using. So we're not going to quite call that one done yet. But let's get our CI set up. So again, I can go back to this project because I've worked with this project before, and I know that they have Travis set up already. So we are going to be very thankful for that, and we are going to borrow their Travis YML. And let's see, touch dot Travis. Actually, I need to do this up one level, don't I? Because this is a project inside of a project. So let's touch Travis.yaml. And refresh folders, there it is. So we're going to use Rust. We don't actually need this. We do want to build on all platforms, and we do need to install our Rust target. I don't have a build yet, but we're just going to do a cargo build. Yeah, I think this should work. Manifest path. What is it? Sensor node cargo.toml. So right now we don't really have any tests, but we should do a build, and we have what we need. So let's go ahead and we might need to change in this directory because this .cargo lives one level down, and I'm wondering if it'll pick it up. But actually, we can test that here. So what if I just run this from this directory before I waste time setting this up to the continuous integration server? Let's see what this does. So if I'm here, it's either going to complain. It's going to say, hey, you know, you're on x86. I don't know what you're talking about. Or it's going to work. One of the two. Compiling always goes a little bit slower when you're streaming because we're using a little bit more of our CPU actively. But the fact that it's rebuilding this makes me a little bit worried because that means that it's probably trying to build in another directory, which is not what we want. So what I'm probably going to do is I'm going to change the script to change into that directory and then just do a cargo build. Let's go ahead and do that because I'm pretty sure that's what we actually want. And just cargo build. No, that's enough for now. Let's see that. Get add -I. Yeah, we changed some stuff, but most important is this. So git commit add CI. Hopefully this is the only one we need. Almost always when I write CI, I push it the first time and it's broken for like the first 3 commits. But let's go ahead and push this up to the repo. Cool. And I've got a link to our repo here. So let's go to this, and then in our commits, we will probably see, ooh, good, we got the yellow dot already, which means that Travis has picked that up. It is queued. Hopefully this should kick off soon. So these are maybe running. Okay, cool. So they've started to run. So that's going to take some time. So let's go ahead and start working on other stuff while we're waiting on that to build, because that's probably going to take a minute or 2 for each of those builds. Oh, we can watch it. We can see how that's going. So you probably will never see the stuff behind me again because right now I'm traveling on a business trip and I'm in a random hotel and I'm actually about to fly back to Berlin today. But, you know, I was up early. I figured I might as well do this. So let's take advantage of some jet lag and figure out what we're going to do here. So this is building, so that's good. So I'm pretty happy that this is going to work fairly well. So let's go ahead, and the other thing that I want, let's see, I put in some templates for using the RTFM protocol, but I never finished this up. So this is a note to myself that I need to rebase this. But I can just borrow this for right now. So let's go find a good demo. So we know that we're going to want this RTFM library. So again, that's that sort of real-time operating system, but not quite. But we'll get to that. And because now I'm thinking about it, let's go ahead and clean this up. I go back and forth whether I like doing this or not. But I've decided. I think .1. I think there's a .1 release of this. I don't want semi-hosting yet. Semi-hosting is useful because it's kind of like being able to print to a serial port, but over the debugger. And the nice thing is it requires none of your hardware to actually work except for the debugger, which is really convenient when you're bringing up the system. The downside is it's incredibly, incredibly slow. Like it takes hundreds of milliseconds to send messages that would take microseconds to send or nanoseconds to send. So I know that this is what I need, so I'm going to go ahead and pull in the RTFM library, and let's see if we can change our blink from a normal, this is our scheduler as a loop that runs as fast as we can, to an RTFM example, although then we're going to make it a RTFM loop that runs as fast as it can. But let's pull this in, and this uses a macro called app, which is nice because it's essentially a declarative way of specifying the structure of your program. And by doing this, the upside is the compiler can now understand what the structure of your program is, and it can make sure everything that you're doing is safe. So we are going to do that. So we don't really need an init yet. Well, let's go ahead and put it there. Init. And also we're going to need to pull in the pack from there, but that exists. So the pack is a peripheral access crate. So this is all the low-level, really low-level register level stuff. So a hardware abstraction layer is a higher level thing, like send these bytes on this serial port, where a pack is like put these bytes at this memory mapped register location. So it's a much lower construct, but we'll see. I can't remember if this works or if I have to explicitly pull in the crate as well, but we will find out because it will either build or it won't. So let's have an init function, and for now let's have an idle function. So if you used Arduino, this is kind of like setup and loop, I think they call it, except for our loop doesn't loop. It just gets called every time our processor is bored and doesn't have anything else to do. So I guess it doesn't get called. I guess it only gets called once because it has to diverge. So let's just go ahead and put our init, and then let's move this here for now. It's probably not the best way to do it. There are better ways of doing it, but this will work for now. And then we get rid of this for now. So let's see what it thinks of that idle. Idle needs to return some kind of type, doesn't it? So let's do that. And we can see that at least the first CI job passed. Cool, all of our CI jobs passed, which means we have built decent code, minimally acceptable. So let's do a cargo build and see what it thinks of that. Cannot find cargo toml, right. That's probably a good thing. Let's make sure it actually, yeah, cool, build actually worked. Sometimes, let's see. Yeah, it's not gonna let me use this, so we're gonna have to explicitly pull this in, because otherwise it doesn't know what crate we're talking about. So we are going to pull in the pack crate, and I know this happens to be version 0.7 because we just had an update for it. I'm a contributor on this repo, so I know we just had an update of this. So let's do that, and then in our main, let's, instead of doing it there, let's make this a use statement. So what's did you mean? Oh, right, underscores and dashes. In Rust, it is very common to specify packages as dashes, but dashes are not a valid name, so they get automatically converted into underscores, which is great, except for, oh right, the pack didn't get updated. Only the hardware abstraction library got updated, so this one's still 0.60. We just updated the hardware abstraction layer. Cool, and it's telling me I don't need my main anymore, the entry macro, which is true, because now RTFM is handling that for me. I don't directly need to use Cortex-M. Actually, I should probably remove that from my list of dependencies, because that's just managed for me now. So yeah, let's go ahead and do that. Let's keep it clean. So I don't think we need this, maybe. Okay, yep, because that's going to be provided already by the DWM 1001. We only needed it in case we needed to directly call it out. So let's go ahead and do a cargo run again. So that's loaded. Ooh, interesting. We have a very solid light. So let's see what our software is doing now. So sig trap breakpoint. This sounds a lot like our processor halted. Mon reset. So now let's actually do that debugging thing. So let's put a break at the main. Let's continue. Yep, we're getting that panic. So let's try that mon reset. Now we're in our main. Let's step in. So this is actually starting. This is grabbing the peripherals. Ah, right. RTFM automatically gets the peripherals for you. So what's happening is we're getting into our main, and I try and take the peripherals again. And I bet you if I step, it's going to say it's going to return a none, which is not good. So we actually do need to go do things the right way. So let's look up RTFM Rust, because there is a template for doing this. Let's see, do I have another template where I thought I had a UART template which says how to do this. Right, it provides it as just the word device. So there's a little bit of magic in there, but instead of having to take this, everywhere that I do this, I just have to type device instead, and then I can get rid of this line. So let's see what it thinks about that. Device, not found in scope. Does it magically take the device? Where do I talk about device? Device equals NRF. Yeah. Cannot find. Ah, right. That's only presented to the init. So I actually do need these resources. So RTFM has this cool way where you can essentially, they're sort of globals, but they're thread safe globals. So we're going to have our static. Right now we just need, what do we need? We need our LED and we need our timer. So static mute. You know what? I know that I've done exactly the right thing here. So I'm going to take this, and there's probably a timer in here, and it's going to tell me what type it is, and static mute timer is a timer. This equals parentheses is saying that you don't know what these are at compile time, or you know what they are, but you won't get them until runtime. So in here, we need to do that, and we need to set. Let's see, look at what my init does, because at the end is where we set all these things. So let's say timer equals timer, and what do we have? We have LED red1 equals device dot LEDs dot D12. I think this is the red LED one. It was certainly red. So I've got that. So now my idle is going to definitely need some of these resources. So idle, I need to tell it that it's going to have resources sources equals timer LED red 1. And I can't remember, does init need to specify what schedule? No, it doesn't. It just gets what it gets. And this device.leds.d12 becomes, what is it? Resources. Does it? What's the syntax for this? It's been a minute since I've used this. Right. It essentially gives me a mutable pointer to it, so I have to dereference it so that I have it. So I do that. And the delay, I need to give it. This mutable reference should just be resources dot timer. Okay, what does it think of this? It is severely unhappy about this. P0 pin output, right. There are some types that are specified that I have not pulled in. So this is why we have examples. So we need to pull in some stuff from the HAL, like the P0 pin and output, and this is probably push-pull. Yes. No P0 pin, right, because this got updated where this just becomes pin now. Pin is private. Okay, so let's go ahead and do a cargo doc, which is going to build the docs for me, because like I said, I opened this PR a while ago and I never closed it, and this is biting me. So timer, expected 1 timer argument, right, because we are going to be using timer 0. So I need NRF pack. Let's just use it here so it's more clear. I need, what do I need? I need timer 0. Timer 0, because this is defined as a low-level item. And it's saying that you need to say what kind of timer it is. And I'm going to say it's a timer backed by timer 0 on the actual hardware. So this is building. And I'll show you what the documentation looks like for this. But it's really nice and it's really handy and it's all offline. So I'm going to get on a plane in a couple hours, and when I'm on the plane, I'll be able to look at all this. Although I probably won't, because I'm probably going to be sleeping. And I'm going to try and stream all the work that I do on here, so I will try not to touch it on the plane. But if I wanted to touch it on the plane, I could touch it on the plane. What else am I going to need? Let's see what else it was complaining about. It was complaining about pin, because pin is private, but there's probably just another place that this is exported now that I don't know where it is. But while this is building, I can go and look. So in my notes, I have a link to the hardware abstraction layer that we're using. So I'm actually going to look at a closed pull request, because I know this was recent. Some stuff has changed. Well, I don't know exactly where it is. So let's just go look at the code. So this is in the common of the HAL. So the nice thing about this HAL is it supports all 3 different versions of the NRF52, the 810, which is the really cheap one, the 832, which is kind of the jack of all trades, the one that we're using, and the 840, which is the expensive, powerful one that has things like USB and stuff in it. But this functionality is common to all of them. So let's, it's probably just in the GPIO, well, pub struct pin. Is that not what I typed? Right, I need a HAL pin, not a pack pin? No, yeah, GPIO. Right, it's not in P0 anymore, it just lives in the GPIO module because it used to be in port 0, but then we had multiple ones. And even the docs are complaining about that. P0 pin, and I gotta get rid of that. Because, yeah, we used to support P0 pin specifically because we only had the 832 support, but the 840 has multiple ports, so we refactored that to be just a pin interface. LEDs in peripherals. Right. Because we're trying to use the board support library. Okay, so I need to look at how that is done. Interesting. Okay, so what's going on here is RTFM assumes that you're just going to give it a hardware abstraction layer, and it's going to work with the hardware abstraction layer. However, for the DWM 1001, we've been very handy, and we've provided a board support package where we provide one function that takes all the pins in all the places that they're supposed to be, and it gives them to you so you don't have to go find them yourselves. However, now we have 2 people trying to be helpful at the same time, or 2 libraries trying to be helpful at the same time, which means that that's not going to work. Let's go look at DWM 1001 crate. Do they have a method that lets you provide the peripherals manually? If they do, then we're good. Pub fun take self new. Okay. Is new. Oh, great. Cool. Okay. So instead of take, we're going to do. Where do I do take? Take. Right. So this is going to be a DWM 1001. So let's do that. So we're just going to have another resource, which is static mut board, which is going to be a DWM 1001 object. That's going to come later. And instead of doing just a new, which I think I even cut that code out, I'm going to do a device timer 0 dot constraint. Is it complaining about that too? No, it's not. So that's going to be right, which is nice. But it's not going to like me doing all of that. So we're going to have to do some shenanigans here. So let mut board equals DWM 1000 new, and we've got what? Device core peripherals. So it's going to take core peripherals, which I don't remember what that's called, but there's going to be something. And then we're going to give it device, because device is actually the peripherals. And that's going to be an option self. So we are going to go ahead and delightfully unwrap that. And then we're going to let's get rid of our timer for right now. That's not actually going to be very useful, but we will have it. And instead of having lead red 1, we're going to have our board. So this goes back to being board.leds.d12.enable. And we need to figure out what the core peripherals are. So we can look at RTFM docs, and then the app attribute, and we're going to look for core. No, it's just called core. Cool. So core, and then we get rid of both of these for now, and let's character constant must be escaped. Oh, it helps if I use the right syntax. Burp, burp, burp. This resource has not been declared. It sure hasn't. So let's get board. Burp, burp, burp. And can't do this. And board equals board. Burp, burp, burp. Board. Not found in this scope. Right, board, because it's resources.board. Build, found. So this super isn't going to work because RTFM gives us peripherals that don't have all of the peripherals in them. They only have some of them because RTFM takes some of the peripherals. So you think I would have run into this before. Okay, so for the sake of time, I'm going to end up filing a PR for the upstream project. So actually, let's go all the way back to what we had a second ago, and we can do this manually. So none of the board stuff, but I need to put a note to myself to file an issue where we need to have an RTFM mode where not everything is available. Okay. So this looks about right. But we still need our GPIOs, so we are going to go look at WM 1001. We are going to go look at what it does for the pins. So we're going to kind of copy and paste some code here, which is unpleasant, but it's going to be okay for this first demo. And then pins. Where else do we use pins? Really should just go look for the LEDs, I think. LEDs. Here we go, LED new. let's see. We're actually going to use the LED type from DWM 1001 because I hope this is a public type. And then D12, what were we doing before? You're going to complain that the type is wrong here anyway, so let's go ahead and, just make that nothing. And you are going to be that. Burp, burp, burp. P.P0.split right, because it's not called P, it's called device. This is the danger of copy and pasting code. Method new is private. Really? Really? Fun new. Okay, well, won't use the LED. So this is going to be that is a pin output, and that is just a pins dot degrade. It's not pins. Pins equals P0 split, right? It is a pins. Push, pull, right, because I have to into push, pull, output. Because I bet you that they're doing some magic here in fun new. Into push, pull, output. And let's start with high. Poop. And then it's not going to have enable and disable, but instead it's going to have, see, enable is set low because this is an active low, and this is going to be set high. Use undeclared level because that comes from GPIO. Cool. Hey, cool, so we get some blinky lights. So now we have working RTFM. Although, this is making me feel like I forgot something because I could have sworn that I had been doing way more complicated things using the DWM 1001 dev kit. So now I'm wondering if I gave up too easy and cut and run when I should not have cut and run. How do I do this on the templates? Do I really? Because I think there's a UART one in here. No, I guess I never used the board support crate. I guess I just used this. DWM 1001. Yeah, I never used that. Okay, cool. I don't know what I was thinking that day, but that's going to be an issue. So what is it complaining about? I definitely saw some warnings. I don't need either of these for right now. Mutt timer. I guess our timer doesn't even exist yet, but that's okay. Well, no, it just doesn't have to be mutable. So let's do that. And you don't need to be mutable. Does that need to be mutable? You do need to be mutable. So this one needs to be mutable, but the other one doesn't. Because in this function, it doesn't have to be modified, but once you have it somewhere else, it does. Cool. All right. Well, what else did we have in here on things to do today? So we got the CI set up, got the HAL and RTFM set up, and we got the first LED set up. So overall a successful day, I would say. So let's go ahead and get at I. We've got all kinds of new things. Actually nothing new, just updated things. git commit. This is move over to RTFM. Don't use the BSP object. Okay, that's, struct. This isn't Java. We sort of have objects, but don't really have objects. Git push origin master. So this is going to kick off our CI, and I think that is a good place to wrap up for today. So we have achieved, let's see, what have we pulled off of this list? We have CI, which is nice. I guess that's the only thing. I didn't have blinky lights in here, so we'll have to save the wireless communication for another day. But we were able to go and add some things, and we have CI, so that is working. So where is my commits? So again, this is the Fair Systems Internet of Streams. Probably the one thing that I will do off of the stream is I will put in a README that talks about what I'm doing here. So most of the things that are in here, how you can follow along, probably links to the YouTube videos once the YouTube videos are actually up. I am going to be planning on streaming this on YouTube, maybe Twitch, but probably YouTube, and then uploading all of the recorded videos to YouTube. So that will all be there. I'll also have a contributing section in my licenses and things like that. For contributing, I will be very welcoming of PRs, so if you're following along and you want to contribute some code, you're welcome to. Just with the caveat that if someone submits a PR, I will probably review the PR on the stream. So if you're not okay with me reviewing your code on the stream, probably don't submit the PR, but feel free to message me. I should put my contact info in there, but I'll put it in here right now. But contact info. So as a reminder who I am, I'm James Munns. If you use Twitter, I'm BitShiftMask. On Twitter, on GitHub, I'm just James Munns. And if you want to send me an email, just send me an email at james.munns@ferrissystems.com. So whether you're interested in the tutorial, the stream, or if you're in a company that's interested in using Rust, interested in learning about Rust, or you need some help with something you've already built in Rust but it's gotten away from you a little bit, feel free to reach out. We're happy to help out with a bunch of those things. So let me go back to the CI and see if our CI is built, and if our CI is built, then that is a good place to wrap up. Pull request, build history. Cool, it's been going for 2 minutes, so it should be very close to done on all of these. So if you have questions, feel free to open up an issue here. I'll probably start opening a bunch of issues for stuff that I plan to do, just to kind of track it in my own head. But if you have questions, feel free to open up an issue or get in contact with me in any of the ways that I listed here. Yeah. So we're waiting for this build to build, and as soon as this goes, then we are good to go. We got 1 green. Two green. All green. Perfect. So that was a successful day. Thank you for watching, and hope to see you all soon.